January 2007, A2 Module 4 paper, question 6. Okay. So we're going to use Coulomb's law for the forces between points, charges, and there's Coulomb's law there, to express the unit of the epsilon naught in terms of the SI units. So essentially what we're going to have to do is say, well, if F is equal to 1 over 4 pi epsilon naught times Q1 Q2 over R squared, therefore epsilon naught is equal to Q1 Q2 over 4 pi F R squared. And what we're looking for now is the units of these. This is a charge, okay, and we're looking for base units. So base units for charge will be amp seconds. Q equals IT, so amp seconds. So we've got amp seconds, amp seconds. I'm not worried about, okay, it's not an equation, I'll just say that's implying this. So 4 pi, no units for that. Force, okay, well, force is newtons. Newtons, F equals MA, so that's kilograms meters seconds to minus 2, F equals MA, and then we've got R squared, so that's a distance which is meters squared. So now what I've got here is I've got amp squared, seconds squared, kilograms to the minus 1, I'm just taking what's on the bottom line here, kilograms to the minus 1, meters cubed, so it's going to meters to the minus 3, s to the minus 2 when it comes up is going to be s squared. Therefore the units are going to be amp squared, seconds to the power of 4, meters to the minus 3, kilograms to the minus 1. So amp squared, seconds to the power of 4, meters to the minus 3, kilograms to the minus 1. Whatever order you give those in. 2 point charges of magnitude 3 microcoulombs and 6 microcoulombs are placed 30 millimeters apart. And if I calculate the magnitude of the force between them, well, F is equal to K Q1 Q2 over R squared, so that's equal to 8.99 times 10 to the power of 9 times Q1 is 3 microcoulombs, that's 3 times 10 to the minus 6 times 6 times 10 to the minus 6 over, and the distance is 30. So that's 30 times 10 to the minus 3, and that's all squared. Fill those in, and what we find is that's 180 newtons. So a force of 180 newtons between those two. When they're free to move, the charges accelerate towards each other, so state what sign each charge could have. Well, that would be positive and that one could be negative, or it could be the other way around. Whatever way, if they're attracted to each other, they must be opposite charges, because opposite charges attract, like charges would repel. There are a number of differences between the electric field produced between two parallel plates with a PD and the field around a point charge. Describe the difference between the electric field strengths in each case. Use diagrams. Right. Probably the diagrams are the most helpful, because if we take a look at a point charge, so if this is positive point charge, then what happens is the field lines are a radial field. So we're getting field lines which are radiating out from that like so. And because it's a positive charge, then those are moving out like that. So it's a non-uniform field, the field lines getting further apart as it goes out. For a positive plate on the top and a negative plate on the bottom, then what we get is equally spaced parallel field lines, like so. And it's the direction a positive charge would move, curved just outside those fields. Okay. So what's the difference? Well, between parallel plates, so between parallel plates we get a uniform field. So the field is uniform. And for a point charge, the field is proportional to 1 over R squared. And also decreases away from the point charge. Now, essentially I think the diagram shows this. You can see here as you're going away from this, we're increasing separation, therefore field strength is declining. Here, uniform, equally spaced, therefore it's a uniform field all the way through. So between parallel plates the electric field is uniform, and for a point charge the field is proportional to 1 over r squared, and so decreases away from the point charge.